Yeah, it's okay. Mm-hmm. Thank you. And this can advance?
You can use this tablet. You can change here.
Okay, fine.
Oh, the point.
Wait a second.
You need to take care with here.
Okay, fine. Mm-hmm.
Muy buenas tardes, tengan todos ustedes muy bienvenidos al Salón de Seminarios Emilio Rosenbluth del Instituto de Ingeniería. En esta ocasión nos acompaña el profesor Patrick Poltre, quien es profesor de la Universidad de Sherbrooke en Canadá. El profesor Poltre tiene la cátedra de Ingeniería Sísmica y Dinámica de Estructuras. Obtuvo su licenciatura y sus grados de maestría en la Universidad Politécnica de Montreal y el grado de doctor en la Universidad de McGill. Su trabajo de investigación está centrado en la dinámica estructural, así como en el diseño de estructuras de concreto ante sismos, el comportamiento de los mismos en general y el monitoreo de la integridad y la salud estructural de edificios. Ha sido autor de 3 libros en análisis y en diseño de estructuras. Es miembro distinguido de la Sociedad Canadiense de Ingeniería Civil, del Instituto Americano del Concreto, así como del Instituto de Ingeniería de Canadá. En el año 2015, el profesor Poltre recibió el premio Armand Frappier de Quebec, que es uno de los premios más importantes que otorga el gobierno de Quebec a las personas que participan o que cultivan el área de las ciencias. Y recientemente, en el año pasado, 2018, fue nombrado Caballero de la Orden Nacional de Quebec, que es uno de los premios, distinciones más importantes que otorga el gobierno de Quebec en Canadá. En esta ocasión, el profesor Poltre nos va a dar una conferencia sobre la amplificación no lineal de modos superiores en edificios a base de muros de concreto y con muros de concreto acoplados, de manera que es para nosotros un privilegio el poder contar con él. Está de visita en México, vino a una visita académica con la Universidad Autónoma de Guerrero en la bella ciudad de Chilpancingo, y de ahí pues viene a la Ciudad de México nada más un par de días a darnos una conferencia y se regresa a Canadá el domingo. Así es que pues muy bienvenido, muchas gracias, thank you very much, welcome. Su conferencia será en inglés y bueno, pues adelante, thank you very much.
How long is the presentation?
40 minutes.
Okay. Thank you very much for the presentation. I didn't understand anything, so I hope it was not too bad. I will be doing it in English. My Spanish is really, really bad. So I'll be talking about higher mode effects on shear. And it's a problem that is recognized for a long time, but without really any solution. Now, you have to realize shear walls coupled or shear walls are the most used structural system in Canada. Probably 95 to 97% of all tall buildings are with a wall, a core, and some coupled walls. And we have examples of shear failure. They are rare, but you can find some. Actually, this one here in Chile and in Japan. And you might have seen also, that it's not shear failure of walls, because that building had a number of shear walls. There were some problem with them, particularly they were too thin and not well designed. In Canada, we use capacity design, where you have a ductile, some are in French, you have a ductile link that will protect all the fragile system. When I say fragile system, I would say shear is a fragile failure, and you want to avoid that. So flexure will be the mode of failure that you will be looking for. In Canada then, we will design a wall to have a plastic hinge at the base and couple walls with plastic hinges at the end of all coupling beam before having hinges at the base of the walls. And if you look at the simple seismic force distribution, this is the factored bending moment, and you have the factored shear. When I say factored, it's the elastic force times a factor that is usually larger than 1. Now, when we do the design, we will calculate the reinforcement here, estimate the probable moment resistance, which is calculated with yield stress equal to 1.25 Fy. Having MP here, we would increase the shear by that ratio of the probable moment resistance divided by the factored moment resistance at the demand, actually, at the base. And in 1995, following New Zealand code, it was said to increase again the shear by a factor beta V. The problem with the Canadian code is that they said to increase it, but they didn't give any formula. So nobody knows what to do with that type of thing because beta V doesn't have any value or any reference to calculate it. So it was recognized in one paper in the 1970s that you might actually, even though you design under capacity design principle, you might have yielding higher up, not only at the base, but particularly for what we're discussing today, the shear would be larger than even the one that was amplified. And it was not really recognized why we had that increase in shear when it would have been limited actually by the capacity of the wall at the base. And later on it was recognized that it's due to the higher modes that you would have that increase. In 1984, the Canadian code actually changed, and instead of calculating the probable moment, what we do is design for the moment resistance here, and then keep the same amount of reinforcement over the plastic hinge zone, calculate the moment resistance at that point, take the ratio of that moment to this moment here, let's say it's about 2, and increase all the bending moment by the factor you obtain at the top of the plastic hinge, so by 2. Having done so, you would increase also the shear diagram, again, by multiplying by the probable moment resistance divided by the demand at the base. And this is the design shear that you would use to design your wall. Let me skip all this and just mention that in Canada, there are really 2 zones of seismic activities. In the west, Vancouver being the highest risk in Canada, and you have Montreal here with the highest risk in the eastern part. The difference between the earthquake waves propagate at a very short distance in the west, and in the east, they would propagate at very large distance. Any earthquake here would propagate up to New York and Boston or even Philadelphia. And also, there are contribution of higher frequency in this zone compared to the west part of Canada. So we have to take care of both areas, west and eastern and western Canada. So let's look at shear walls first. And we considered the western part first. What we did is actually try to see what are the most important characteristic on the amplification, on the shear amplification. So we studied different type of walls, number of stories, fundamental period, aspect ratios, flexural overstrength at the wall base. Flexural overstrength is the probable moment divided by the demand. Could be between 1.5 to 3 or even 4. And, and site class varied actually from A, C, D, and E, and wall cross-section that you have here, as you have here. Actually, we found out that only the period of vibration will control actually the response. So that's one particular parameter that we have to account for, and flexural overstrength need to be accounted for. And what we did is then, I didn't mention it, but let me get back. We have a building with a number of stories ranging from about 5 to 40 stories. And we actually model it with two computer programs, with OpenSeas here and with Vector 2 from University of Toronto. Vector 2 has interaction between flexure and shear. So it's way better actually than OpenSeas, which doesn't have interaction between shear and flexure. And we have a concrete strength of 40, Fy is 400, and we varied rho according to what we would have in practice. 10% of axial load is usually what is the axial load acting on walls. Pitot effect was accounted for, and damping we took 2% for the first and the last period of vibration of importance. For the earthquake, we started about 10 years ago, I suppose, by using generated earthquakes by Atkinson, but we changed after that. And as you can see here, what you would have is the probable shear resistance, and we would find that the shear is larger than that, and we will call that V dynamic. And we can then estimate the amplification factor, omega V, which is the ratio of V dynamic divided by V probable. We can calculate that at the base, or we can calculate that over all, take an average over all stories. Very quickly, we found out that those factors didn't influence quite a lot, except that for gamma W less than 2, we would have hinges forming somewhere else from the base. But if you have gamma 2 equal to 2 or larger than 2, you would not have yielding higher up. So really, one thing a designer could do is just start by designing with gamma W equal to or even larger, and then you will not have to consider yielding at the height. And you can see here, again, different influence that we obtain. Actually, this is the moment demand, and here the shear demand, as you can see, it varies quite a bit with gamma W, the overstrength factor. Anyway, the important thing is that graph, where depending on the period of vibration, this is number of stories, because in New Zealand they work with number of stories. But if you consider the period of vibration from 0.5 to 4, and you see here the dynamic amplification factor, it's larger than 1. Most of the time it will be constant over the range of period here, larger than 1. So having done that, we proposed that to the Canadian Code, and they adopted it somewhat because they limited it to 1.5, whereas you could have it even larger than 1.5, say 2, or even going to 2.5. Let me skip so I don't overdo the time that was allocated to me. So the capacity design method prescribed by the CSA produce envelopes that are significant, that underestimate the demand. So you might have potential risk of shear failure, and then you need to use an amplification factor. The important conclusion is that for a period larger than 1 second, if you have gamma W equal to 2, you don't have to worry about yielding of the wall higher up the height. And the thing is, we did it for Western Canada first, so we have to do it for Eastern Canada. And then we started again. I didn't mention it, but the total number of analysis we did for the Western Canada is over 10,000 analysis. And we did the same thing here, over 10,000 analysis, because you have a number of buildings. You have about 40 different time history to consider for each building, and you have different soil classes, you have different gamma W, so it's a very large number. So we had to use the parallel computer that is at University of Sherbrooke, and we could do it in a reasonable amount of time. So this is the spectrum for Western Canada. It's in Vancouver. So we had to find a site in Eastern Canada that compares with the western part, and we chose Rivière-du-Loup to put the buildings and do the analysis. I'm sorry. This is kind of sensible. So the spectrum are compatible, not in the frequency content, as I mentioned, because higher frequency content can be found in the eastern compared to the western part of Canada. Again, all the analyses are showing that you do have amplification and formation of plastic hinges higher up if gamma W is less than 2. If it's larger than 2, then not a big problem. We do have shear amplification. The difference actually is that we have shear amplification even for very short building compared to Vancouver, for example. And again, as you can see here, we do have possibility of yielding at somewhere along the height of the wall. Again, at 1 here is yielding, so at the base we do have a plastic hinge at the base, but we can have yielding here when you have gamma W less than 2. So this was the first proposal for the west part of Canada. Again, as you can see, there is an increase up to 1 second, and then about constant from there on. Same for Eastern Canada, although I'm not showing it here. We do have contribution between 0.25 and 0.5, which is different than for the west part of Canada. So this is what, from the result we obtained, this is what has been adopted in the Canadian code. It's something that is equal to 1 up to 0.25, increase linearly up to, say, 0.5, and then kept constant over the range of lateral period, here, but limited to 1.5. That is, you cannot have the factor larger than 1.5. As I mentioned, we found in our analysis that you can have factor of 2 or 2.5. So coupled wall was not considered. Why? Because it was thought that coupled walls are like frames, and we haven't seen any shear amplification in frames. So it was decided not to have amplification for coupled walls. So I decided to have a look at it and see what is going on. I remind you that for coupled walls, yielding is at the end of the coupling beams before you have yielding at the base of the wall according to capacity design principles. And I can see that because that's basically what you have seen before. That is, this is the actually probable, and then when you do the analysis, the average and plus or minus 1 standard deviation, it's quite larger actually than the probable shear resistance. Let me quickly mention that when you design in Canada, the V, the design, shear design, is equal to V elastic. That some formula that are very close to whatever you have in different countries, divided by RD and divided by RO, as opposed to United States, we have two different factors. These are ductility-related factors varying from 1 to 4. And RO is the overstrain factor that would vary between 1 and 1.7 at the best. So for ductile coupled walls, RD would be equal to 4 and RO 1.7. For partially coupled walls, 3.5 and 1.7. And for shear walls, 3.5 and 1.6. So this is actually the formula that has been used in the Canadian code. And we did some parametric study again to see the effect of all those parameters, and then after that conduct the study, retaining only the most significant parameters. So this is the set of data that we use. Degree of coupling is the moment taken by the axial load acting on both walls divided by the total overturning moment. And it varies between 30% to 75%. When you reach 65%, below 65% in Canada, we call that partially coupled walls. Larger than 65%, it's coupled, fully coupled ductile walls. And overstrain varied between 2 to 4. But as I mentioned before, we use the uniform hazard spectra to generate the earthquakes. But it was actually recognized that this is not very good to use that type of signal to make the studies that we did. So we changed actually, and what we are using now is the conditional mean spectrum, where you condition the time history that you will be using on a specific period. Usually it's the first period. In that particular case, we would use the second period. But we would also condition it on a minimum and a maximum value at 1 or 2 standard deviation. So we would have some good match of the time history compared to the spectrum that should be used for the area. Okay, this is the number of shear walls, partially coupled shear walls, and coupled shear walls. That's under 10,000 analyses. So roughly 30,000 analyses were done to get that thing, to get a good handle, actually, of the phenomenon. And for the coupled walls, actually, we use OpenSys only because Vector 2 could not do it because of the coupling beams. So we had beam with concentrated hinges at the end, and for the walls, we use layered analysis. With different sort of stress-strain relationship for steel and concrete and cyclic behavior. The conclusion, the amplification vary with the degree of coupling from 30 to 45, that is actually reducing again at 50 and 60. And actually at 70, we would have quite reduced value around less than 1.5. And then the amplification factor, when we look at it against the fundamental period for the West and the East, we have about the same tendency, a little bit larger for the East, and here contribution of higher mode even for short buildings as opposed to the western part of Canada. So there is some change to be done on the code. I hope in the next edition of the code we should have it. And the amplification as a factor of degree of coupling, as you can see here, start at a constant value and then reduce with increasing degree of coupling. It's an easy thing to fix because you just have to enter that parameter, and the parameter depends on if you have a shear wall, a partially coupled shear walls, or a fully coupled shear walls, and depends only on the degree of coupling. And hopefully, I think that can cover it, except that the 1.5 maximum cap value that we have in Canada, I don't think that's good enough. And then the expression that I mentioned for eta here can be found very easily here, depending on gamma W, and the degree of coupling. So this is the numerical analysis. I don't know much study that has been carried out for the experimental verification of what we are talking about here. Numerical studies, the first one actually that inspired the modification on the New Zealand code was by Berkeley et al. Then there is a set here. The one that I did is this one here, this one, and this one. So there's a large number of numerical simulation. And for experimental studies, I do know only really one by Libas from University of Illinois. So, and it was by accident because he tested a small scale coupled wall system and saw that the shear was larger than what it was expected to be. So really, let me make it very simple. When you have a linear, let's say you have a triangular load, seismic load applied to your building, the resultant will be at a certain height, RE. When you have yielding at the base, the distribution would change, and that force which was there would change location to another place, going lower, which means the moment is still the same because that force increased, the R is reducing, but the force times the lever arm here will be equal to that. However, shear will be larger because that force is increasing because of the reduced lever arm. So the thing that we decided to do is do a hybrid test, and we designed a building, 8-story building, and that part, we kept it elastic, although I mentioned it could have yielding, we kept it elastic, and the base over the height of the plastic hinge, we would test it in the laboratory. The two are actually linked. We will be analyzing this with the computer program. It's linear, and this will be tested in the laboratory. So let me quickly move to the experimental verification. Actually, what is going on is you're modeling this, and this is the equation of motion. There is a link between the two. I don't know if you're familiar with hybrid tests. And that part here, the stiffness matrix times the displacement would give you the force that will be input back to the analysis. You would feed actually the displacement that need to be imposed horizontally. It's not an easy test to do. Actually, it's a very, very complicated test and took us a long time before we could fix everything. So really, what is going on here, you take the time history, you send a displacement, send that displacement to the jacks here and to the two vertical jacks that are there to move horizontally and rotate the building or the wall, then measure the force in all 4 jacks, send it to the finite element program, which is here, calculate displacement, velocity, and acceleration, go back here and keep doing that in a loop and progress in the test. So really, we had a building with 1.2 second. As I mentioned, it's a single shear wall designed according to CSA 822.3 2014, which is the latest edition of the code. This is the real size building, and the reduced size, it's about 1/3. And we had a base that you can see here, 800 millimeter, 2.7 meter. This is the wall that will be tested, and we have a top here, 450 millimeter. It's high strength concrete because we didn't want to have any problem in the head and concentrate on the wall. So we have 2 boundary elements here with concentrated reinforcement, distributed reinforcement according to the Kenyan code, and horizontally distributed reinforcement also that are well anchored according to the code in the boundary elements. This is the base. It's pretty big, actually. Specimen is the reinforcement for the base before casting. And this is after casting the base. This is the wall without the head. We will cast that later on. In the back, this is a masonry wall that we would be testing later on. And for the test, there is a set of computer programs that need to be used, actually. OpenSys is the main finite element program that is analyzing the top part of the building and predicting the displacement. OpenFresco actually take those values and then transfer them to LabVIEW. LabVIEW actually transfer those to the controlling system, which is an MTS control system, which impose the displacement, get back to OpenFresco, and OpenFresco send the result to OpenSys, and that is being done in a loop. The trouble actually is that connection point here, which need to maintain compatibility between the two. If it was still, it would be easy, because when you have cracking, there's a problem, because the neutral axis move from one point to the other, whereas OpenSys actually consider that the rotation is about the center of gravity. So we had a big problem there. The other problem is that it's very stiff at the beginning. When it's cracked, it's become very flexible, and control is a little bit tricky at the start. So we had to control that point here. So what we did, actually, first of all, let's look at the equation of motion that you have here. There is only one mass in direction 2, which is M2 to here, which will give you a damping matrix, which is proportional to M and K. So there is a term that is here and another that is there. And that one will cause trouble. Why? Because we don't have that displacement in the vertical direction, and then we need to remove it, because in OpenSys, the point of rotation doesn't move up and down. So we cannot have a velocity and a displacement at that point. So what we did, actually, because Fy, the vertical load, need to remain constant, we had to kill that term that is here. How we did that? By putting a zero-length element of constant stiffness, not in the experimental part, but in the numerical part. And because it's constant, the force, the axial load, will remain constant. Then we just have to verify that we have equilibrium between the two vertical actuators. So that's what I explained. And then the trouble is we need to find, at each step of the analysis, we need to find where that neutral axis is. That's a very complicated problem, actually. So what we did is, while we are doing the analysis, we are actually calculating the curvature, getting the rotation, and obtaining the position of that neutral axis. Having it, then we can correct for the displacement that need to be there at the center of gravity of the wall. Because really, the zero displacement is here, not over there. So this is the setup. We have a top beam here to impose vertical axial force and also rotation while we're testing, and two horizontal actuators that are putting the shear into the, and bending moment into the wall. We had actually to control the error and then also correct for when we have to stop. I don't want to go into that. It's kind of very complicated. But anyway, from OpenSys here to OpenFresco, we are solving, introducing the demand, seeing if we need to correct. If we don't need to correct or we need to correct, we have to go up here. And again, verify that we have equilibrium between the vertical actuators. If we have equilibrium, we can move up and then go back and then start the loop again, like that. This is the numerical part. This is the test part of the experiment. The problem is sometimes you need to interrupt. One test would take more than 1 day to do, maybe 2-3 days. So you have to restart the next day. So we had to develop a restart procedure. that I don't want to get into really. Or if it's interrupted for any reason, we have to restart it again. So we develop a method of actually starting the test after some interruption. So this is the setup here. That's the reaction wall. This is the strong floor that we have, and everything is from MTS, the latest version of flex test that we are using. And I mentioned that. This is the final setup, as you can see here. The wall, it was heavily instrumented to measure even the displacement at the base of the wall. All the reinforcement were also instrumented and instrumented with X gauges here and horizontal for shear. And this is the way we perform the test. TCP/IP connection, send the command to the test specimen, calculate, and we have to make a correction for the scale factor also, by the way, I didn't mention that. Then scale up the results, move it to the computer to do the finite element, and keep doing the test that way. What we did is use 3 different motion, GM0, which is a very small earthquake that we use just to make sure that our test setup is functioning properly. GM1, which is actually the design earthquake level, and GM2, which is a much larger one and shorter. So when you compare, actually, you have to compare the command and what is measured, and as you can see, we are doing pretty well in terms of controlling the displacement that we are imposing on the specimen. Again here, comparison between the command and the measurement here for the GM2 motion, and same for the GM3 motion, so we do have a good control of the system. This is what we measured actually, yielding in all longitudinal reinforcement. At GM1 and GM2, you start having yielding of shear, all horizontal reinforcement actually. Remind you, this is about the length of the plastic inch that we consider in Canada. Actually, we do have yielding even higher up the plastic inch that is considered in the code. Now, let's look at the result. Capacity design, we have 21,000 for moment. Maximum demand is 32, and maximum demand for GM2, which is a very large earthquake, is 26. Now, it's surprising that is less, but remember, we have yielding occurring here, so we are actually reducing stiffness and everything, so the demand is less here. Shear, we have measured at maximum moment 3,700 kilonewton and 7,160. Remember, capacity design should limit the shear to 2,500, and we are measuring actually 7,000 for shear or 5,000. So factor of 2 to even close to 3. So amplification for GM1 certainly larger than 1.5, and for GM2 about 3. These are the analytical results that we use to predict the amplification. And as you can see here, prediction is pretty good with experiment, which is the design earthquake level, which is here. For the large earthquake, it could go very high, even to a factor of 3. Now, and that's a nice thing that we could actually now prove why we do have shear amplification. If you enlarge that section of the result, which is here, and at the moment where you have maximum shear or maximum moment, you do have different sign for the moment at the base and at the top of the wall. And here again, you have at the base here and the top, the moment are in opposite direction, which means it's not the first mode that is controlling the shear, but the second, maybe the third mode that is controlling the result. And this is pretty clear here, because at maximum shear demand, as you can see here, it's not the first mode that we are having here, but certainly the second mode that is controlling the result. Same result. We did calculate the contribution of the different contributors to the displacement at the top. So displacement due to elongation of the bars at the base, it's the first part that you have here. Not significant, but still you need to consider it. And sliding also. Rotation at the base is that. Flexural displacement is that contribution here, and shear is not negligible at all. There are some errors, evidently, in the measurement. Actually, here we don't have the 100% that is required, and here it's a little bit larger than what is supposed to be. I don't know how do you make a movie. Nope. Does it move? Oh, okay. Actually, it's not really a movie. It's pictures that we took because one test is about a week. We could not film that thing. So what you see here is pictures at different time during the test, with large shear opening here, flexural yielding, and shear controlling the behavior of the wall. We did actually some pushover at the end, cycling at two times at the same level, but that was just to verify the capacity of the wall. At some time, you would have buckling of the longitudinal bars and breaking of some transverse bar in the concentrated zone, crushing of the concrete at the end of the walls. And this is the cyclic behavior that was measured. If you compare prediction with test result, we do have very good argument. Not perfect. OpenSys is certainly better than Vector 2 is certainly better than OpenSys at predicting the result, but the two give quite good result. Again here, with some discrepancies at the end, but reasonable in terms of result, as you can see here, even for the GM2 motion. Conclusion, we need to account for shear amplification. It's something important. The thing is, the design for shear is very conservative. That's why you don't see problem coming out of more buildings during earthquakes, but need to be accounted for. And factors limited to 1.5 in Canada, it's limited to 1.8 in New Zealand. I think it's a little bit low. It could go to 2, and I think at 2, I would probably be myself more happy. Future research. One thing that is interesting us right now is the behavior of the secondary elements. That is, the shear wall or the coupled wall are usually used as the primary seismic force resistance, and all the beams and columns are considered secondary elements that need only to take the gravity loads. However, you need to find the displacement. It's not easy. Even in ASC 7 and ACI dimension to do that calculation, nobody really knows how to calculate that thing properly. We have published 2 papers on that subject. And the next thing we would be doing is a distributed test where the shear wall will be tested at Sherbrooke and the columns and beam will be tested in 2 different universities, plus the numerical model will be running at the same time. I think I would stop here. Can you show the second PowerPoint file? It's a very short one. It will take 2-3 minutes. Okay. Okay, so that's we have two laboratory at the University of Sherbrooke. Oops, what's going on? Okay. The picture that was there, I don't know why it went. But we did, we tested a full-size two-story buildings with high-strength concrete. That was the picture that you saw a moment ago. And we did for damage detection. So we were loading with earthquake forces at different level, and each time we would test the structure dynamically to obtain damping and frequencies, and from that we could predict where the damage were. That was the first laboratory. That's the second laboratory with two walls. Those are 12 meters high and very large, strong floor. And we have a very, very big machine here, 12,000 kilonewton. Actually, it's dynamic also, MTS. Everything actually in the lab is MTS, which makes us a very like client of MTS. This is a dynamic press here, 700 kilonewton, high frequency, and another press, which is here, a smaller one, to test cylinders. Okay, this is then the wall in the other laboratory. This is the building. It was 3 meter high, 4 meter perpendicular to the longitudinal direction, 5 meter here. The mass there, it was tested under pseudodynamic tests with 1, 2, 4 jacks. You can see the size of the specimen when considering the person that is sitting there. Is 2 meter high, actually. So you saw that wall. We have also set up to test cyclic tests of reinforced concrete columns. And this is the latest test we have been doing, considering that gentleman is from Colombia, so speaks Spanish. Considering his height, he is about 1.8 meter, about my height. You can see the size of the column, actually, and the diameter is about 900 millimeter in diameter. We have a shaking table, not as big as what you have here, 3 meter by 3 meter, still an MTS machine, unidirectional though, and we are developing some dampers to introduce between the diagonals that you have here. Well, that was something that my head of department asked me to present to you. It's in Spanish. We have two groups, civil engineering and construction. It's the only university with those two options. We do actually have a wind tunnel, and I think that's about it. If you have any question, please, I'll try to answer. Let me mention that I'm quite honored to be in a room named after Emilio Rosenbluth. This would be the highlight of my career. I hope you know who that person is. Good.
Thanks for your presentation. When calculating the displacement demands to be applied to the test unit, in this hybrid test, you do some analysis where there is a need to use some values and model for the damping. So the question is, how sensitive could be the experimental results to the different assumptions of damping? For instance, you are using Raleigh. Some people suggest using constant damping and almost very close to zero sometimes.
Okay, it's a good question. And every time I submit some papers, there are always questions about damping. And people would ask, why are you not using 5% damping or even 10% damping? There are two damping there. There is intersect damping, which we tested under dynamic excitation. It's about close to 1% to 2%, never higher than 2% actually. And I could show you some result, but we don't have time. So really, the question is, do you keep the damping constant or do you use, say, Raleigh damping? I use Raleigh damping. It's 2% fixed at first, and say if you have a 40-story, it's at 40 period. So the rest is pretty reduced, less than 2. But you could use a constant value. If I'm using a constant, I would use maybe 1% damping for that. The rest, the damping, the stochastic damping, will come out from the test result and the behavior, nonlinear behavior of the building. I don't know if I answered your question. Yes?
Hi. This is regarding your hybrid test. You deal like almost quasi-static test, right?
Yes.
Yeah, because it's kind of pseudo-dynamic, but it's, I mean, the time that you spend doing that is almost quasi-static. Are you running any tests to compare that result with an actual real-time hybrid test, or compare it with a shake table testing? Have you done something like that? Because you conclude that it's pretty much the same.
Yeah, we haven't. Are we going to do it? I don't know. I don't think there is a big influence for reinforced concrete. Big influence of the speed of or the rate of loading. I would think it's minimal, maybe close to increase in modulus of elasticity. That's what we're doing right now, testing structural elements under dynamic loading in real time to see what is the increment of the modulus of elasticity when you have dynamic loading, and also increase in concrete strength. So for that particular test, it's not very important. But if you are testing, say, rubber bearing, you need to do that in real time because the behavior change with the excitation and completely. So in that case, you would need to do the tests in real time. So there are tests that you need to do in real time, and some other quasi-static tests are pretty reasonable.
Okay, thank you.
Thank you very much for your presentation. Probably I missed, but what was the resistance of the concrete that you used and the resistance of the steel, of the reinforcement? I mean?
For the wall, 400 megapascal for the steel and 40 megapascal for the concrete, for the wall. But the tall building, the tall specimen, the two-story, we used 70 megapascal concrete at the time. It was done quite a bit of time ago, where we were developing new regulations for high-strength concrete in Canada. And also, you might not have noticed, but the work what we did actually was adopted even in ACI, in the latest version of ACI, for the confinement reinforcement, up to maybe 120 megapascal. And actually, Sherbrooke is known for the material part also, because that's probably where high-strength concrete was really developed in North America long time ago by Berclaudet Sin.
Hi. My question is about the factor of amplification due to the higher modes. Here in Mexico City, the soil is very soft, so these higher modes represent a risk. Maybe I have to worry about, or maybe only the first modes that represents almost all mass of the building in a couple wall.
Well, that's a dynamic question. There is never one answer for a dynamic problem, because it's related to the frequency content of the accelerogram and the frequency content of the structure. But if, for example, like in 1985, where you have a period of 2 seconds, mainly for the earthquake, buildings with two second period will be mainly dominated by the first one, so the higher mode won't contribute too much. So it's really a dynamic problem. You have to consider both the frequency content of the earthquake or the spectrum, and the frequency content of the building to design.
Okay.
But one interesting thing here, for me, if I was in an office building, the first thing I would do is fix gamma W to 2. That is, make sure that at the base, you have twice the capacity, twice the capacity of the wall at the base. Having done that, you can control the distribution of flexure over the height of the building, then amplify for shear. And I think that would be a pretty nice design of a shear wall, if the steps are followed that way.
Say that your recommendation is to fix or use lower ductility at the base and maybe increase?
No, the ductility we choose, certainly in Canada, we choose first. A ductile coupled walls, we have RD equal to 4 and RO equal to 1.7. So you divide basically by 8, like you have in ASC 7. Having done so, you have to design now your walls. I would myself design for overcapacity of the wall at the base, right from the start, and eliminate all the other problems that we identified that is very difficult to control. If you are yielding up the height of your wall, it's a big problem for shear and flexure, actually.
Thank you. Thank you so much.
Gracias, thank you very much. I will give you a little token of appreciation from our institute. This is a diploma that is signed by our director that explains that you gave us a lecture title of the lecture and the location, obviously in Spanish.
Thank you.
And this is just a small memento for you to take to Canada.
Okay,
And
thank
we
you.
hope to have you again in Mexico. We hope also to have some of your students here in Mexico and our students in Sherbrooke.
Yes.
So we look forward to establish a cooperation. I think the research that you do is very significant, not only for Canada, but for Mexico, because of the questions that you saw. We're very interested and the problems are quite similar. So we look forward to establish a cooperation.
Thank you. And to all the students, you're all welcome in Sherbrooke. We speak English and French. You usually Spanish-speaking learn French quite quickly, in about 2 months. So you're all welcome.
The only question is, what is the temperature?
I had to give a presentation in Chilpancingo, and I said I was happy to be here because it was -2 in Sherbrooke. But the question is what the temperature is sometime in January or February. -30 is sometimes possible. And this year we had snow every day, so snow at home was about that high. But it's fun, I can tell you. You learn to skate. The students learn quickly to skate, and they learn to ski. 20 minutes from the university you can ski. So about, and even we do have a ski slope right in the middle of the city. So you'll enjoy it if you come. Thank you.